All right, let's take a look at this problem. Here we are told to find both the Thevenin and Norton equivalents at terminals A and B. So terminals A and B here, we want to find V Thevenin and then R Thevenin, and then we're going to find I Norton and R Norton. Okay, so this is what we're being asked to find. Now, before we move forward, we know from the equations and rules before, and we're going to take advantage of this, is that R Norton is equal to R Thevenin. So that's going to make our approach a little easier. And if that's the case, we're going to take this here to find V Thevenin, and once we find V Thevenin, we can just simply use Ohm's law, V equals IR, to find I, which is going to be our I Norton, and I'll show you that at the end of this problem. Okay, so just keep that in the back of your mind. The other thing I want you to know is that in these problems, it's best to, there are several ways to solve this problem. There are more complex, longer ways, more traditional ways, but I want to show you one of the quicker ways of doing it, and that is when solving for the equivalence, solving for R Thevenin or R Norton. It's usually the best way to do the resistance first, okay, to find the resistance first. And to do that, the rule is to find the resistance is to take your original circuit, which we're going to take into consideration later, and turn off all the independent sources. So we have this 1 amp, we're going to turn it off, which equates to an open circuit here. The 14 volts, a voltage source, is going to equate to a short circuit here. And then this 3 amps is going to equate to an open circuit here. So what that does, it drastically simplifies our circuit. And now we have a circuit where we need to find the Thevenin equivalent resistance across AB here. So now we can find R Thevenin looking in this way. Okay, so to do that, it's just a matter of putting all those resistors together. So if we look at those resistors together, we have 14 and 16 are in series. Okay, so we got 14 plus 6 is going to give us 20 ohms. Okay, and then from there, the 20 ohms is going to be in parallel with the 5 ohms. Okay, so now we have R Thevenin is equal to 20 ohms in parallel with the 5 ohms, and then we just do the math, 20 times 5 over 20 plus 5, and if we plug that into our calculator, we get 4 ohms. So we've solved for R Thevenin. Okay, so we've done the first part. All right, so now what we need to do is go back to the original circuit, which is this guy here, and then solve for V Thevenin, which is going to be across AB. So now we need to know what V Thevenin is. Okay, so to do that, there are a couple ways of doing it. I'll just do one example. So let me go ahead and scroll up. I'm going to copy this guy, put him down here, and just start with this problem here. Okay, so what I like to do is I like to go ahead and define the currents. And how you define the currents is up to you. So you can choose which direction you want to assign the currents and how you want to set up the problem. So I'm going to just assume I have a current coming in this way from this 1 amp. I'm going to assume my current direction is this way. I have a current going in that way, my current going down here, and then I have another current going down here. Okay. Other thing I want to do is I want to define my ground node or reference node. I'll say it's right here, and that's going to be my V I'm going to call this V, which is going to be equal to 0 here. Technically this is VB, but it's also going to be 0. This is we'll call VA. Okay. I'm going to call this VC. So if I have VA, VB, I'm going to call this guy VC. And then we have VC, we have 14 volts here. So technically, if we really want to break this down, right here, this is VC plus 14 volts. Okay, just keep that in the back of your mind as we do potential nodal analyses. Okay, so from here, let's look at KCL. So KCL, and we're going to look at KCL at node VA. And remember, to do that, we want to look at the currents going in should be equal to the currents going out. Okay. Now, one thing to note is at VA here, this is all the same node. Okay, that's the same node there. Okay. So let's write this out. I have this guy, this current going in, which is VC plus 14 minus VA over 14 ohms. And that's what's going in. What's going out are the 3 amps, which is 3, and then the current going through the 5 ohm resistor, and that's just plus VA minus VB, but VB is V, which we set as 0, minus 0 over 5 ohms. Okay, and now it's a matter of simplifying this equation. It's a matter of simplifying it. So we can multiply it by some factor. So I multiply it by some factor. Let's just say I multiply this by, or put it in terms of ratios. So I'll multiply it by 70. And that's going to give me 5 VC plus 70 minus 5 VA is equal to 210 plus 14 VA. We further simplify it, we get 19 VA plus VC equals 140. And we can say this is one equation that we want to keep when we're trying to solve for this. Okay, so next what we want to do is look at the nodes, do KCL at VC. So we need enough equations to solve for these variables. So at node VC we have this guy coming in, this guy coming out, and another one coming out there. Okay, so I'm gonna say my current here, so if you look at it, we have 1 amp. Okay, so 1 amp is going in is equal to, we have VC right here, VC is going out, VC minus 0, VC minus 0 here over 6, VC minus 0 over 6, plus VC, okay, VC plus 14 minus VA, because we have VC and then we got that 14 there and minus 14, so it's going to be VC plus 14 minus VA. We defined that previously, over 14, and then we can multiply this by some factor to simplify, and we get 84 equals 14 VC plus 6 VC plus 84 minus 6 VA. Okay, and then we rewrite this and we get minus 6 VA plus 20 VC equals 0, and this will be our second equation, and we can solve for simultaneous equations there. Plug this into our calculator, and then what we'll get is we'll get VA is equal to minus 8 volts and VC is equal to minus 2.4 volts. Okay, now if you go back to this, VA is just VA, this VA minus VB, which essentially is our Thevenin here, but we said VB was 0, so our Thevenin is essentially going to be minus 8 volts. So Thevenin is equal to minus 8 volts. Okay, so now we've solved for both the current, Thevenin current, and Thevenin voltage. Okay, so let's go ahead and draw that Thevenin equivalent circuit. There's a couple ways we can do that, but because this is a minus 8 volts, I'll show you. I can draw this as, I can flip the signs, minus plus, and we have a resistor there. Okay, we have our nodes A, B. Our Thevenin is going to be 4 ohms, and then our Thevenin is going to be 8 volts. Or I could have flipped the signs and just said minus 8 volts. Either way works. Okay, so this is the Thevenin equivalent. As I mentioned before, because we know this relationship here, R Norton is equal to R Thevenin, so technically we've already solved for the second part of the equation, or the problem. We know that Rn is just going to be 4 ohms, and using Ohm's law, because the next thing we want to do is we want to find I Norton, and we just say V equals IR, so we rearrange the equation. V In is just going to be VTH over RTH. We know both of those, and that's minus 8 volts over 4 ohms, and that's going to give us minus 2 volts, or excuse me, 2 amps there. Yeah, watch our units, minus 2 amps. And then so now we have our I Norton is solved and our R Norton is solved, and we can redraw this circuit. Note with the current source, it's going to be in parallel with the resistance, and then we have our A and our B here. 2 amps here is our I Norton, and our R Norton is 4 ohms. Again, we could have redrawn this arrow up and said -2. Either way works. Just be consistent with the way you are labeling your circuit, and that's how you solve for this problem. That's this one way. There are other ways of doing this. Another way you can consider is doing source transformations. Consider this, transforming this guy using source transformations to a voltage source in series with a resistor, and consider doing that. That would simplify your equation, your circuit, and you can solve it that way. I'll leave that up to you to work on that.